Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the fourth lecture of this week. So let us continue with the discussion that we already started in lecture 3. If you recall, this is the overall philosophy of finite element method. We had already discussed this, and we had also discussed that the element formulation, the step 2, this step is the most important, and it requires, and the rest of the course we will be talking about mostly on element formulation. It depends on what is the governing equations, what kind of problems you are doing. So now, but then for some simplified system, this can be done directly. Okay, for instance, these are, if you take these some example like this, for these systems, these element formulation, element level equations can be obtained directly, and we have been doing that exercise. Okay, and what is the example we have taken to demonstrate that? Let us take this as an example. Okay, so this is called direct approach. The reason is we compute. By the end of this exercise, we'll automatically realize why this approach is called direct approach. The element level equations we can obtain directly from the basic knowledge of our mechanics and equilibrium, compatibility, constitutive relations, and so on. So take an example like this. It is a bar element. Bar element means you have only degrees of freedom along the axial direction, means axial deformation takes place, and therefore the forces in the member in the structure is along the axial direction. Either it is axial compression or it is axial tension. Okay, and we had already now this is important. You see, in the very first day, when we were mentioning the steps in engineering analysis, we saw that idealization is an important step. We have a physical system. From the physical system, you have idealization. Okay, or in this case, I would rather say the computational idealization, because at the end of the day, all these computations to be done on that idealized system, right? Now, you see on your screen, this is the physical system. The first one is the physical system, and on your screen, this is one idealization where the entire system is idealized as a three-dimensional object. Okay, so therefore you model the cross sections, length, everything. And in the second thing, though this is a 3D idealization, in the second case it is 1D idealization. If we find, for this case at least, that our deformation is in the axial direction, and we are interested to find out what is the force, axial force in the member, and then what is the reactions. We are not very much interested to find out what happened across the section, how the stresses are distributed across the section, deformations are distributed across the section. If you are not interested in that, then we can go for 1D idealization. But these are two different. For the same problem, you can get a solution, rather approximate solution, by idealizing this as a one-dimensional problem, and then the same problem can be solved by idealizing this as a three-dimensional problem. Now, another level of idealization you can do, that is, for instance, if you look at this, this problem is axisymmetric. Axisymmetric in the sense, if this is the axis, this is the longitudinal axis of the bar, then along with respect to this axis, this is symmetric, right? Now, if this is symmetric, then there is another concept called axisymmetric formulation. In this case, so this is x, suppose this is your, this is longitudinal axis is x, and this direction is r directions, okay? So, this another idealization you can do as like this. So, this is your x and this is your r direction, and this idealization will be this. So, this is your model and this is subjected to a load like this, distributed load like this. And then you discretize this model using either quadrilateral element or two-dimensional element, either quadrilateral element or say triangular element. We can discretize this, say for instance, if we discretize this as like this, we can discretize, okay. These are all discretization with two-dimensional element, triangular element. So, this is another idealization. This is another idealization. So, this is 2D axisymmetric idealization. 2D axisymmetric idealization. Now, when you analyze the structure, we need to decide what idealization is suitable in the context of this analysis. And this idealization, again, let me repeat, this idealization, what idealization to be followed, what idealization to be taken, that depends on what is our expectation from the analysis, what are the features that we want to find out from the analysis, okay. Now our objective here is not to get a solution of this problem, rather our objective is to understand the steps of direct approach, and through this direct approach we'll also have a better comprehension of the overall philosophy of finite element method, okay. Now, so let us take this, the 1D idealization of this problem, okay. So, this is, we'll take this idealization. Now, you recall in the last class we have seen that so if we take this idealization, then essentially this, if we take a single element, any element in 1D bar, then we have seen in the last class that this is element level, these are the forces and the displacement at the element level. So, if the element is any arbitrary element is named as E, which is a two node, 1 and 2 are the nodes, and then if one is the force at node 1 and E superscript, it means that this is force, this force belongs to element number E, and if 2 is the node, is the force at node number 2 and superscript E, implies that it belongs to element number E. Similarly, U1E and U2E are the degrees of freedom at node number 1 and node number 2 respectively, okay. Now, so we have also seen in the last class, okay, so so we have also seen in the last class that this is the element level formulation. Element level formulation means this is how the forces and the displacement at the element level are related to each other, right? And this is called element stiffness matrix. Ke is the element stiffness matrix, and Fe is the element force vector, and UE are the element level displacement vector. And if you recall, the expression for Ke was this Ke was AE by LE. Okay, this was the expression of Ke. Now, next is if we have this, this is the expression we have already seen, and this is called element stiffness matrix. So, this we have seen in the last class. Now, what we will be doing in this class is, once we have this element level formulation, a general expression for stiffness matrix, we will see how to discretize this problem, how to divide this entire problem into small subdomains, write the equations, these equations for each subdomain, and then assemble these information about the element level information, and then finally get a solution of this problem. So that exercise we will do now. Okay, so so this is our problem, and suppose this is the idealization we have now. Now, let us divide the entire problem into two elements. One is this one and another is this one. So, this is say element number 1, and this is element number 2. Okay. If you wish, you can divide it into 4 elements, like this is, you can divide into 4 elements. This is element number 1, 2, 3, 4. Or if you can divide it into several other elements, like you can divide with any number of element, okay. So, for all these elements belongs to this portion, their cross sections are A1, and for all these elements belong to this section, their cross sections are A2, and for all the element belongs to this one, your length of the element will be, these will be the length of the element, individual element. Here also these will be the length of the individual element. But then for demonstration purpose, let us divide the entire structure, in this case bar, into 2 elements, and these elements are like this. So, for this, from here to here 1 element, from here to here 1 element, and from here to here another element. So, this is 2 element, right. So, if you divide in 2 element, you have a node here, you have another node here, and then you have another node here. So, this element is connected. So, say this is element number 1 and this element number 2. These elements is connected between this node and this node, and this element is connected between this node and this node, and this is shown here. Okay. Now, so next, so this is, suppose this is element number 1 and element number 2 that we have already discussed, and then these are the node number 1, node number 2, and node number 3. Now, what information we have here? You see, these are the information we have. E1, E2, E3 are the displacement, the degrees of freedom at node number 1, node number 2, and node number 3. Okay, and F1, F2, F3 are the external forces applied on this structure. For instance, if we take this example, where yeah. So, if there is a load like this, if there is a load like this, suppose P1, and if there is another load like P2, then what will happen? We can say that F1 is equal to the external load, which is P1, and F2 is the external load P2. So, F1, F2, F3 are essentially the loads on this external load at that joint. Okay. And then because of this external load, there will be reaction. If you draw the free body diagram, there will be reaction here. Say this reaction will be R. This reaction will be R. So, we can say that F3 is essentially the reaction. So, these are F1, F2, F3. Now, once we have this, now let us see what is the element level, your diagram. So, for element 1, this one, for element 1, you have F1, E1, and then you have F2, U2. These are the and then for element level 2, these are the forces and displacements. Okay. Now, this is a general expression. Now, looking at this, what we know is, so this expression we have already seen for the given element. Now, let us map this expression with this. If we map this, then what we have is E1 dash is essentially E1. So, this is E1, and U21 is essentially U2. Similarly, U12 is U2, and U22 is U3. So these and these are essentially same, but now here the displacements in the actual problem is explicitly represented. Okay. Now once we have that, now we know that for element number 1, then forces and displacements are related like this, right? Forces and displacement are related like this, and K1 is the stiffness for K. Expression of K1 will be what? Here expression for K1 will be A1 L1 by E1 or yeah, L1 E1 by E1. Okay, and similarly if we write K2, expression of K2 will be expression of K2 will be A A2 E2 by E2, A2 E2 by A2 E1 by L1 and E2 by L2. Okay, so these will be the expression. So this is element level expression we have, element level equations we have. Now next is we need to, once we have these element level equation, we have to combine them. Okay, how to combine them? Let us see that. So okay, so this already we have seen. Now this is important, next step is important. You see, this assembling part, this combining these element level information can be done in another very straightforward way. We'll come to that, but just to understand that this, when we assemble them, by assembling we also need to respect the equilibrium, compatibility, constitutive relations, all these fundamental these properties that need to be respected, and how during assembling that is being respected, that is being preserved. That's why we are doing this exercise. But as far as the assembling is concerned, once we understand that, assembling can be done in a more straightforward way. We will see that as well. Okay, so you see this expression now can be rewritten like this. Okay, so idea here is to, at the right hand side, here you have U1 and U2. At the right hand side you put all these degrees of freedom, U1, U2 and U3. So you see there is these two equations are essentially similar. These two are essentially similar, but written in a different way. Where now similarly, this is also can be written like this. These two again same, but then U1, U2, U3 here and U1, U2, U3 here. Now once we have written this like this, then the advantage is that if we can directly see this and this adding would have been difficult, because here it is U1 and U2, here it is U2 and U3. But in this, if we write this expression like this and like this, now we can add them, because here also it is U1, U2, U3, and here also it is U1, U2, U3, and the similar order. Okay. Now before we add them, now as I just now said, when we assemble them, the properties, the equilibrium, compatibility, these properties are preserved. So let us go with the property, see the equilibrium equations and compatibility equations, and then see what happens and how this assembling can be done. So this is the example, this is the problem. Now we have F1, F2. Now since we are writing the equilibrium equations, I removed U1, U2, U3 in this diagram. It is how the forces are related to each other. So F1, F2, F3 are the external forces. Now we'll write equilibrium of the joints and equilibrium of the member, both. Now let us do that. So you see, these are the member and these three dots are the joints. Let us write the equilibrium. So members are equilibrated like this. Here it is F1 E1, here it is F2 E2. The forces in this member like this, and similarly force in member number 2 is like this. Okay, we have already seen this. Now from the second diagram, the equilibrium of these member and these forces acting on this entire diagram, the external forces, try to see what would be the free body diagram of the joints. The free body diagram of the joints will be this. So first joint we have external force F1, and then the nodal internal forces is F1 E1. Mind it, if in the member, if it is in this direction, this force is in this direction, then you have a node here. So on the node, the force will be in this direction. That's why if F11 is shown in this direction. Okay, note it will be in this direction. Now similarly, if you have a node here, now the F22 on the member in this direction, it will be in this direction here. It will be in this. It will be in and this will be in this direction here. And similarly, you have a node here. This will be in this direction here. So let us draw the free body diagram of node number 2. Free body diagram node number 2. You have an external force F2, and then the forces are internal nodal forces are this one. So this and this balance each other. So this and this balance each other, and this and this, they balance each other. So at that particular point, your internal, these two forces balance each other. Only force you have the external force. If there is no external force, then it is okay. Now similarly, if we draw the joint for this, external force is F3, and then this is your internal the nodal force. Now once we have all this free body diagram, let us write the equilibrium equations on this for this free body diagram. And equilibrium equations will be for this. Equilibrium equations will be this. So this internal force will be F1, and which just by looking at the diagram we have already seen that. We have already we intuitively we can say that. Okay. Now equilibrium equation for node number 2 will be this, and then finally the equilibrium of node number 3 will be this. Now once we have these three equilibrium equation of 3 node, let us then combine them. Let us see what happens, how we combine them. Now this, if we combine, this will give this. Okay, there is a reason why it is written in this fashion. Okay, we'll see the reason shortly. So this gives you essentially same thing. F11 is F11 will be F1, then F21 plus F12 is equal to F2 the second, and the third one is F22 is equal to F3. So these three equations and these are same. Now once we have this, let us see what we can do further with this. So we have now this. This is our this we have already seen. You remember element level equations. Now element level equations are expressed in this fashion, so that we can add the forces like this. And this is the equation just now we have derived in the previous slide, this one. Now if we combine them, you see now this is essentially this. So this is essentially this, and this is this. Okay. Now if we combine this, then what will happen? So if we combine this, down this plus this, then what we have is like this. So this will be K1, and then this will be minus K1, and then finally this will be 0, and this will be minus K1, then this and this plus we need to add. So this will be K1 plus K2, and then this will be minus K2, and then finally this will be 0, this will be 0, then minus K2, and then K2. This will be the, and then finally this is U1, U2 and U3, and that is equal to, so this gives you actually F1, F2 and F3. So this is our equation for the entire system. Okay, you see we had now since we don't have, okay, now this was the equation, these equation and these equation, these were the equation at the element level, and then when we join them, combine them, assemble them, this gives the equation for the now. So this is assembling. Now once it is assembled, next job is to now solve it. Now what are the informations we have about the problem? Like what are the forces we have on the structure? What are the boundary conditions? The information on the boundary conditions we have means information on U1, U2, U3, or F1, F2, F3. For instance, in this example, we know that U3 will be equal to 0 because this is node number 1, this is node number 2, and this is node number 3. So U3 will be 0 because this is a fixed end. So that information we have. This is the boundary condition. This boundary condition is called essential boundary condition or Dirichlet boundary conditions. Okay. Now, what information about on F1, F2, and F3 we have? If we apply a force like this, suppose this is P1, and if we apply a force like P2, then we know that F1 will be equal to P1, F2 will be equal to P2, and then F3 will be F3 is the unknown, F3 the reactions that we need to determine. So in this case, that U3, F1, F2 all are known. So with this, some informations are available, some variables are known, some are not known. Based on this, we need to finally get the solution of this equation. So we will do that in the next class. Now, another important thing, as I said, these assembling we have done directly from the equilibrium equations, but then the similar exercise we can do directly. We'll see that as well in the next class. Important observation, that is whether it is element level. If I go back, if I take you final expression, if I take you this element level, you can delete it. These are the element level. So this is the element level expression, element level equation. And if you look at, this is the stiffness matrix for the element, for each element. You look at this stiffness matrix is symmetric. If you look at this stiffness matrix is symmetric. Okay. If we see, this is the final, this is the after assembling the stiffness matrix, this stiffness matrix is symmetric. Now, we'll not discuss, it is just an observation, and this observation is not new to you. Similar observation you already had in your matrix method of structural analysis. There also you had stiffness matrices, and you are aware of the properties of those stiffness matrices. Those stiffness matrices were symmetric. One of the property they were symmetric. There are few other important properties as well. We'll see that as we move on. You had also seen in structural analysis the reciprocal theorem, and that also gives you some idea. Now, this is an observation, but why this is symmetric and what story it tells you, I leave it to you. Please think and then find out. And then eventually, as we progress, when we talk about the properties of the stiffness matrix, those things anyway will be discussed. Okay, so with this, let us stop here today. So next class, what we do is, next class we'll see how another way of assembling this stiffness matrix, and then finally we'll see how to solve these equations. Okay, with that, let us stop today. See you in the next class. Thank you.